Hi everyone. In this video, we're going to discuss partial fractions decomposition. In particular, you're going to see how to rewrite integrands and how rewriting them in particular ways can simplify the process of integration. We'll learn how to rewrite rational functions as integrands in a way that makes integration easier. And then we'll utilize earlier integration methods to integrate these rewritten integrals. So to start, let's consider the following integral. So imagine you were asked to calculate the integral of 3 minus x over x cubed minus x dx. So let's think about the methods we know and maybe why they're not such a good fit. So the first trick that's always available is maybe we could simplify this integral somehow, right? So I could look at this and notice that, well, I could factor an x out in the bottom. That would give me an x times x squared minus 1. And I can actually factor x squared minus 1. So I could look at this and say, oh, I could actually factor this denominator as x times x minus 1 times x plus 1. And it would be nice if that would cancel with a factor of the top. Notice that this x does not cancel with this x because x here is not a factor of the top. It's just a term in this subtraction. So I can factor it, but that doesn't actually help me simplify the integral. I'm not going to get some nice cancellation that will make this easy. So just straight up algebraic manipulation, always great when it works, but it's not going to work here. And then we can start running through our methods. What about u substitution? Do I see a function and its derivative sitting here? Well, not really, right? On the bottom, I have something cubed, so its derivative would be like something squared. Up here, I have a linear term. It doesn't seem like that's probably going to work. I could try maybe a trig substitution, but usually for trig substitution, or sorry, I could try by parts. That would be the next one. By parts, I would need a product of things. I could rewrite this as a product, but it's not clear to see how either of those, one might get better as you take a derivative, but the other one's probably going to get much worse as you take an antiderivative. So it turns out integration by parts here is not a great method either. You could think about trig substitution, but generally there you're thinking about having like an x squared plus or minus something. And you may actually, you could try that here because you can factor an x out and be left with an x squared minus 1. Then you could try something like a secant substitution. The problem there is going to be this top part. You're going to end up with like a 3 minus like a 3 minus secant of theta. I actually don't know. Maybe that would work. You could try it, but probably seems a little convoluted at best if it's going to work. But what if I told you that integrand 3 minus x over x cubed minus x is actually equal to 1 over x minus 1 minus 3 over x plus 2 over x plus 1. Now, the first thing you'd say is, well, wait, how on earth did you get there? Well, we'll get to that in a minute. But just imagine that you magically knew this was true. Now this integrand would be very easy to calculate, right? So now if I were to look at this, I can now integrate term by term. This first term, its antiderivative is just natural log of x minus 1. You could do that as a u substitution as you want, although it's probably a little bit of overkill, right? If I take the derivative of natural log of x minus 1, that's 1 over x minus 1 times the derivative of x minus 1, which is just 1. Okay, so I just get this as the derivative of this, so this is the antiderivative, minus the antiderivative of 3 over x is 3 times the natural log of x. So again, you can think about factoring that 3 out of the integral. Integral of 1 over x is natural log of x. And then I would end up with a 2 times the natural log of x plus 1. Okay. Remembering, of course, the all-important plus c. So if I could magically realize that this was equal to this sort of entire expression sitting over here, right? Well, that makes the integral very easy. And again, this is a trick we see time and time again. If we can do some manipulation of the integrand, whether that's a substitution or something else, then it can make the integral very easy to compute. All right. That obviously begs the question, though, how on earth did you get that? Well, let's make one more observation before we move on. And that is, if you remember, when we first talked about this, I mentioned that this actually factors as x times x minus 1 times x plus 1. And if I look here, I see in sort of in turn each of the factors, right? There's the x minus 1, and the x plus 1. And then on the tops, right, I just have a constant, another constant, and another constant, okay? So what I want to try and understand is maybe there's some way that I can understand the form in which I could rewrite this, and then I could just do a little bit of algebra to calculate these constants. Now, all of this is really going to depend on how this denominator factors. So I'm going to break this up into a couple of cases, and we'll start with sort of simplest cases first, and then we'll see that more complicated cases are actually just combinations of some simpler cases. So our fundamental question here is, if I have an integrand that's some rational expression. So a rational expression, remember, is a ratio of two polynomials. So I'm imagining that this P of x is a polynomial and this Q of x is a polynomial. And so I want to know, how do I rewrite this rational expression in a way that might make it easier to integrate? Okay, so I want to break this into cases. So the first case I want to deal with is, what if the denominator, the Q of x, is just x minus some number to some power n? So like, let's say it's x minus 1 to the third, right? In that case, so let's just imagine, right, we had Q of x is equal to x minus 1 to the third, okay? Then what this tells us is that we should be able to rewrite this in the form some number a1 over x minus 1 plus some other number a2 over x minus 1 squared plus some other number a3 over x minus 1 cubed. So I go all the way up. I have a term for sort of each power of x minus 1. And in the numerator, I just have these constants. And now, depending on what P of x is, I'm going to see if I can try to figure out what those constants are. Okay, so let's actually see how this works through a particular example. So before I worry about integration, let me just imagine that I wanted to use partial fractions decomposition, that's what this method is called, to rewrite this rational expression. So I have x minus 2 over x squared plus 2x plus 1. Now, the first thing I want to do is I want to recognize that this is really x minus 2 over that denominator factors as x plus 1 squared. Okay, so what I ought to try to do then, my highest power is 2 here. So I'm going to have two terms. I'm going to have x plus 1 in the first denominator, just to the first power, so by itself. And I'll have some constant there, plus some other constant over x plus 1 squared. And I'm going to stop at 2 because the highest power here is 2. All right. Now the question is, can I figure out what these numbers a1 and a2 are? All right. So in order to do that, what I'm going to do is I'm going to try and multiply both sides here by something that will clear out all the denominators. So in this case, my sort of highest power of x plus 1 is this x plus 1 squared. So I'm going to multiply both sides by x plus 1 squared. Okay. So if I multiply both sides by x plus 1 squared, do that in a different color in here. So I'm going to multiply by x plus 1 squared. I'm going to multiply here by x plus 1 squared. So you'll actually immediately notice here, right, the x plus 1 squareds will cancel, and I'll get x minus 2. And now over here, I need to distribute this x minus 1. So I'll get a1 x plus 1 squared over x plus 1 plus a2 x plus 1 squared over x plus 1 squared. Okay. Those will cancel. Here I'll lose 1 power of the x plus 1 will cancel there. And so I'll end up with x minus 2 is equal to a1 times x plus 1 plus a2. Now, once I'm here, I have a couple of options for actually how to continue solving this. I'll show you both, and then I'll continue using the one that I personally use, although it'll be up to you. So one way to do this, and the way that I prefer to do it, is to look at the right-hand side and say, you know what, I'm going to get all my terms that contain x together and all my terms that don't contain x together. So if I distribute this, I'll get an a1x plus a1 and then plus a2. So my only term that contains an x is an a1x. And then my other two terms, I have a a1 times 1 here and an a2 here. Okay. And now I look at this and I say, well, if these two things are going to be equal, then the coefficient of x here has to match the coefficient of x sitting here, and that coefficient is 1. So that tells me that a1 ought to be equal to 1. If these two sides are going to be equal, then the constant term sitting here has to be equal to the constant term sitting here. That tells me that a1 plus a2 has to be equal to -2. But I know that a1 is 1. So that tells me that 1 plus a2 is -2, which tells me that a2 is -3. So now notice here, I now have values for a1 and a2. And if I go back to my original setup and remember what I was trying to do before I ever multiplied by anything, right? I said, oh, I'm trying to find a1 and a2. Rewrite that. So that's where I started. I was trying to find a1 and a2. Now I've found the values of a1 and a2. Okay? So I can just plug them in up here. So a1 is now 1, and a2 is -3. All right. So I've done no calculus. This is all purely algebra, and this is algebra to rewrite this sort of more complicated integrand in a simpler form that hopefully will be easier to integrate. So now if you imagine that my goal is to integrate this function, and then if I want to integrate x minus 2 over x squared plus 2x plus 1, I can now instead integrate 1 over x plus 1 minus 3 over x plus 1 squared dx. And now I can do this term by term. The antiderivative of this first term is fairly straightforward. That's natural log of x plus 1. This one may be slightly trickier. As we do more of these, you'll probably become more comfortable with them. But just to walk through it in detail one time. So I'm going to pull the 3 out, and I'll have 1 over x plus 1 squared dx. If I want to, I can think of this as a u substitution. I could let u be equal to x plus 1, and then du dx would just be 1. And so I get 3 times the integral of 1 over u squared du. That's the same as, carrying that 3 along, 3 times the integral of u to the minus 2 du. That's 3 times, now the antiderivative of this is just negative u to the negative 1. So increase the power by 1 and divide by negative 1. It's the same as multiplying by negative 1. And so you get negative 3 over u plus c, but that's negative 3 over x plus 1 plus c. Okay, so now here we had a minus here, so let's be careful. Minus, and then the antiderivative of this is negative, so that becomes a plus 3 over x plus 1 plus c. So again, the key here is do some clever algebra to rewrite your integrand, and now you've broken it up into integrals which are easier to deal with. Again, it's not easy, but easier. All right, let's look at another form of factor we could end up with in the denominator. So it's also possible, so before we looked at linear factor raised to a power, it's also possible to have an irreducible quadratic factor. So by that I mean you have some quadratic factor and you can't factor the quadratic anymore, right? So you can't factor it into like x minus something times x minus something else, right? This is a quadratic that cannot be factored. It doesn't have real roots. But so you have this quadratic factor maybe also raised to some power. Well, in that case, it's almost the same. So if you look at our denominators, we have sort of irreducible quadratic factor to the first power, irreducible quadratic factor to the second power, so on and so on and so on, all the way until we get to irreducible quadratic factor to the nth power. But now in the numerators, right, instead of just having constants, we have linear factors, right? So I have a1x plus b1, a2x plus b2, all the way up to anx plus bn, right? So the setup here is a little more complicated. I have maybe some more factors floating around, but fundamentally I'm going to set it up in sort of the same way. So again, let's actually see how this works in the context of an example. So imagine I want to use partial fractions decomposition to rewrite this 2x cubed plus 4x divided by x times x squared plus 1 quantity squared. Now, important note here, and an important factor in getting this set up correctly to begin with is we're always going to assume that our rational expression is in simplest terms. So in particular, if I look here, the numerator and denominator actually have a common factor here of x. So in the numerator, I could factor out an x, and I'd be left with 2x squared plus 4. In the denominator, I have this factor of x. Okay. And so before I even begin, I want to make sure I simplify and cancel those x's. So I'll end up with 2x squared plus 4 divided by x squared plus 1 squared. Now, that x squared plus 1, that's that irreducible quadratic factor. I cannot factor that any more than it already is. Okay, it's x squared plus 1. It can't be factored anymore. So what I want to do then is now I need to set this up using sort of the structure for irreducible quadratic factors. So I look at this, I have irreducible quadratic factor to the second power. So I'm going to set this up. My first denominator is just going to have that irreducible quadratic factor plus irreducible quadratic factor squared. Now, if this was to the fifth power, I'd keep going. I'd have one that was x squared plus 1 to the third, x squared plus 1 to the fourth, x squared plus 1 to the fifth. I always go all the way up to whatever the highest power that appears here is. Here, that highest power is 2, so I'm done there. And now my numerators So my first one is going to be a1x plus b1. My second one is going to be a2x plus b2. If you read in some other textbook or watch other videos, they could call these A, B, C, and D. You can call those constants anything you want. I like calling them A1 and B1 and A2 and B2 because they sort of help me remember the location and which denominator they go with, right? So the ones go with the first denominator, the twos go with the second denominator. But there are lots of ways to do it, and they're all perfectly fine. All right. Now our goal is to find those values A1, B1, A2, and B2 so that this expression is equal to this. Okay. How are we going to do that? Well, we're going to do it exactly the same way we did before. We're going to multiply by something that will clear all of the denominators. And in this case, that something is going to be x squared plus 1 quantity squared. Okay. So I'm going to multiply here by x squared plus 1 squared. That's obviously, those are going to cancel, right? And then I'm going to multiply all of this by x squared plus 1 quantity squared. So I will end up with 2x squared, make that a little bigger. End up with 2x squared plus 4 is equal to, now when I distribute this here, one of the factors of x squared plus 1 will cancel, but the other will remain. So I end up with an a1x plus b1 times the remaining factor of x squared plus 1. When I multiply here, these will actually both cancel, and so I'll be left with a a2x plus b2. All right. Again, I'm trying to find a1, b1, a2, and b2 here. So now what I'm going to do is I'm going to group my constants by powers of x. So if I look on this left-hand side, I've got a 2x squared. I don't have any x's. And then my constant term is 4. Well, let's look over here. Here I have an a1x x squared. So that's going to give me an a1x cubed. Notice I actually don't have any x cubes over here. Now, over here, let's see, in terms of, so x cubed is my highest power here. In terms of x squared, I'm going to get a b1 x squared, right? b1 x squared. Okay, so that's got this times this, this times this. Then I'm going to get, in terms of x values, I'm going to get an a1x, but I'm also going to have an a2x. So I'm going to have a1 plus a2x. And then my constant terms, I'll get a b1 times 1. So that's just a b1 and a b2. So I get a b1 plus b2. Okay. Now, I did sort of a lot of grouping together all at the same time. If it helps, just multiply this all out and then regroup in terms of powers of x. So your x cubed terms, your x squared terms, your x terms, and then your constant terms. Okay. But now that I have this, I can equate the coefficients on each side. So if I look, my coefficient of x cubed here should be equal to my coefficient of x cubed here. What does that tell me? Well, a1 better be 0. All right. My coefficient of x squared here better be the same as my coefficient of x squared here. That tells me that b1 better be equal to 2. My coefficient of x here ought to be equal to my coefficient of x here. Okay, so that tells me what? That tells me that a1 plus a2 ought to be equal to 0. But wait, that tells me, I know a1 is 0. That tells me that 0 plus a2 is equal to 0, which tells me that a2 is 0. And now if we look at our last coefficient, 4 ought to be equal to b1 plus b2. b1 was equal to 2, though. That gives me that 2 plus b2 ought to be equal to 4, which tells me that b2 ought to be equal to 2. And so now if I look, I now have all my values, A1, B1, A2, and B2. And now I can just plug them in to help rewrite this integrand. Okay. So now at the end of the day, what we end up with is that this whole thing I'm going to sort of just erase this intermediate stuff here, right? And now I can just plug in my values. Well, A1 and A2 are both 0. So they're going to go away. And here my B1 is 2 and my B2 is 2. So both of my numerators here are going to be 2. And I can get rid of that. And so now what I have is that this expression is actually equal to that expression. Okay. So now if I want to integrate, right, now I can just integrate the thing on the left, or sorry, on the right. All right. So now if the problem became integrate 2x cubed plus 4x divided by x times x squared plus 1 squared, I've now done all the work to show that that integrand is actually the same as 2 over x squared plus 1 plus 2 over x squared plus 1 squared dx. Now, here I don't want to emphasize continuing to go through this process. I will point out that if you, well, quickly, if you wanted to do these, this would be 2 times the antiderivative of 1 over x squared plus 1. That's actually tangent inverse of x. Plus, then you'd have this integral, you can pull the 2 out, 1 over x squared plus 1 squared dx. This is actually an integral that you would do a trig substitution on. You would use a tangent substitution, but it's going to become a little more complicated. So I don't want to emphasize that part of it. What I want to emphasize for the purposes of this is the ability to rewrite it. And you do, in fact, end up with something that you could integrate now using a trig substitution. And in fact, I encourage you to give it a shot if you want to practice your trig substitution. All right. So far, we've dealt with really 2 distinct cases here. We have dealt with the case where I have a linear factor raised to some power, and that's my entire denominator, 1 linear factor raised to a power, or when I have an irreducible quadratic factor raised to some power, and that's my entire denominator. But the question is, well, there are lots of other types of denominators. And so in the case 3, basically says, well, if we have a product of linear and or irreducible quadratic factors, you basically just include all the terms from cases 1 and 2 based on each factor, okay? So let's actually see in practice, right, what that means. So imagine I want to use partial fractions decomposition to rewrite this integrand, okay? So if I look at this, I have 1 single linear factor, and then I have another linear factor squared, okay? So in this case, I really have like a combination of 2 case 1s, but these are different linear factors. So what I'm going to do is I'm going to sort of start setting this up, and I'm going to say, okay, well, because of the x minus 1 to the first power, some part of this just needs to be some constant over x minus 1, right? I have some stuff over x minus 1, so I should simplify that, okay? Now, secondly, I have this x plus 1 quantity squared, right? And so to deal with that, right, I should add an x plus 1 in the denominator and an x plus 1 squared, right? It's a linear factor to the second power, right? Linear factor to the second power, so I go linear factor up 1 power, and that's in fact my highest power, so I stop there. And because these are linear factors, these should have just more constants sitting up here. Now, if I want to find the values of A1, A2, and A3 that work here, right, I need to do exactly what I've done before. I'm going to multiply by this entire denominator on both sides. Okay, now I'm going to skip a little bit of a step writing it out, but what I'm doing is I'm multiplying on both sides by x minus 1 times x plus 1 squared. On the left, if I do that, that will leave me with this denominator, or sorry, with the entire numerator. On the right, when I multiply this by x minus 1 times x plus 1 squared, the x minus 1s are going to cancel, and I'll be left with a1 times x plus 1 squared. When I multiply this term by x minus 1 times x plus 1 squared, one of the x plus 1 factors is going to cancel, and I'm going to be left with a2 times x minus 1 times x plus 1. When I multiply this factor by x minus 1 times x plus 1 squared, the x plus 1 squareds will cancel, and I'll be left with a3 times x minus 1. Okay. Now, same thing as before, I want to multiply this out, and then I want to collect powers, common powers of x together. So to do this here, I'll actually sort of write out what you would get in the expansion. So you'd get a1 x squared plus 2a1x plus a1. That comes from expanding this first term. Here you would get an a2 x squared minus an a2. And here you would get just a3x minus a3. Now we're going to group common powers of x together. So I've got an x squared here and an x squared here. So I've got a a1 plus a2 x squared. My x terms, I've got an x term here and an x term here. So I've got a 2a1 plus a3x. My constant terms then are an a1, a minus a2, and a minus a3. I've got an a1, a minus a2, and a minus a3 all together. All right. Now, when I look at this, this is going to become a little bit trickier than some of the other cases. Okay, because now when I start equating coefficients, in the previous cases, when I equated some of the coefficients, they just told me what one of the constants that I was looking for was. Here, that's not going to happen quite so easily. So equating these first two coefficients, I get that a1 plus a2 should be equal to -5. Equating the second two coefficients, I get that 2a1 plus a3 should be equal to -5. And then finally, I get that -2 should be equal to this. So I get that a1 minus a2 minus a3 should be equal to -2. Now, the issue that I face here is that it's not immediately obvious how to get any one of the values out of here, although we will be able to. Okay. So what I want to notice here is that both of these depend on a1. One of them involves a2 and one involves a3. So what I'm going to do here is I'm going to take this first one and I'm going to solve it for a2. So a2 is -5 minus a1. I'm going to solve this for a3. This gives me that a3 is -5 minus 2a1. And now what I'm going to do is I'm going to take those values of a2 and a3 and I'm going to plug them into this last equation, which will give me an equation that's only in terms of a1 now so that I can find a1. Okay, so that will give me that a1 minus a2. Well, my a2 is -5 minus a1. minus A3, my A3 is minus 5 minus 2A1. That ought to be equal to negative 2. Now, if I clean up this left-hand side, I'll get an A1 plus another A1 plus 2 more A1s. I'll get 4A1. And then I'll get a minus negative 5. That's a plus 5. Minus negative 5 is another plus 5. So I get plus 10, okay, is equal to negative 2. Okay. And now if I solve this, I'll subtract the 10 over. That'll give me negative 12. Divide by 4. That'll give me A1. And hopefully you can see this. A1 is negative 3. Hopefully you can see that A1 is negative 3. And now that I know that what A1 is, I can just come back up here. Then A2 is negative 5 minus negative 3. So negative 5 minus negative 3, that's negative 2. So I got A2 now. It's negative 2. And A3, well, it's negative 5 minus 2 times negative 3. So that's going to be 1. That's negative 5 plus 6, which is 1. Okay. And so now I have A1, A2, and A3. So going back to my original problem, I now have A1, A2, and A3. So A1 was negative 3, A2 was negative 2, and A3 was 1. And so now if you ask me to integrate this expression, I would have a much easier time because now I can fairly easily integrate both of these, or sorry, all three of these terms. So now, and maybe I'll just sort of add it here, right? Imagine the problem now is to integrate this, sort of try to squeeze a dx there. I could instead just integrate this dx, right? And now I can integrate this term by term, right? This is negative 3 natural log of x minus 1. This is negative 2 natural log of x plus 1. And this I could do a u substitution on. As I mentioned, we'll be dealing with these fairly often. You would set u equal to x plus 1. This would become minus 1 over x plus 1. And then to wrap it all off, we'd have a plus c. So again, partial fractions decomposition is not really an integration technique in some sense. It's really an algebraic technique for rewriting the integral. It just so happens that it's a really common trick to use to rewrite the integral. So we really think of it as a method of integration, even though primarily it's just about doing some algebra. All right, so we've done a lot of examples. Now it's time for a little knowledge check. So imagine that you're asked to find the integral of 2x divided by x plus 1 times x minus 3 dx. So the first thing I want you to do before you commit to the whole integral is think about whether or not you could rewrite the integrand here using partial fractions decomposition. So give that a try. We'll sort of pause the video here, let you try that. Then we'll come back and talk about the integration. Okay, great. Let's see how you did. So if I want to rewrite 2x divided by x plus 1 times x minus 3, the first thing I have to do is set up the correct form, right? I have distinct linear factors here, each raised to the first power. So I'm just going to get one term for the x plus 1 in the denominator and one term for the x minus 3. Because they're both linear factors, I'm just going to get an a1 and an a2 in the numerator. Now my goal is, can I figure out what A1 and A2 are? So, your first step is always sort of setting up the correct form. Then once you have the correct form, now can we find these constants A1 and A2? So what am I going to do? I'm going to multiply both sides by x plus 1, x minus 3, x plus 1, x minus 3. Okay. Over here, these will just cancel, and I'll end up with 2x. And over here, when I multiply this, when I take both of these terms and multiply over here, the x plus 1s will cancel. So I'll end up with A1 times x minus 3. And when I distribute here, I'll end up with A2 times x plus 1. Now, I'm going to try and, let's see, 2x then, if I distribute this out, I'll get an A1x and an A2x. So I'll get A1 plus A2 times x. And then I'll get a minus 3A1 and a plus A2 for my constant terms. And so now equating coefficients, I have A1 plus A2x here, and I have a 2x here. So I know I need A1 plus A2 to be equal to 2. I also here have this constant term, minus 3A1 plus A2, which I know should be equal to 0 because there's no constant term over here. So if I look at this now, I have a number of options for solving this. And in fact, maybe the easiest thing to do here is to just take the first one, solve it for either variable. So A2 is equal to 2 minus A1. Now I'm going to plug that into the second equation. So I'll get minus 3A1 plus A2, but A2 is 2 minus A1, should be equal to 0. And so if I simplify that a bit, let's see, what does that give me? That gives me minus 4A1 plus 2 is equal to 0. If I move this over, that gives me minus 4A1 is equal to minus 2. And if I divide both sides by -4, I get A1 is -2 over -4, or 1/2. Oh, sorry, be careful there. That's not equal to 1/2. A1 is equal to 1/2. Now that I have my A1, I can come back up here and plug in my A1. So now my A2 is 2 minus A1, or 2 minus 1/2. That will end up being 3/2. Okay. And so what I really want you to see here is that you can rewrite this, and sometimes these constants do come out to be fractions. There's nothing to be scared of in that regard. But now I can rewrite this as the integral of, instead of dealing with this, I'm now going to deal with A1, which is 1/2 over x plus 1 dx, plus the integral of 3/2 over x minus 3 dx. All right, so that's how to rewrite the integral using partial fractions decomposition. Let's now pause a second. I'm going to erase the board, and I want you to just see if you can take this the rest of the way to the finish line and find this antiderivative. All right, so let's see how you did. Even though we have fractions here, they're nice because they're constants. I can just pull them outside of the integral. So I can pull that 1/2 out. I'll just be left with 1 over x plus 1, and its antiderivative is natural log of x plus 1. Plus, I can pull that 3/2 out. It's just a constant. And I'll end up with 1 over x minus 3. And the antiderivative of 1 over x minus 3 is just natural log of x minus 3. And so there is our final antiderivative using partial fractions decomposition. All right. Now, you've now seen pretty much everything to do with partial fractions decomposition. It does require some patience with the algebra. It can be a little tedious at times, but if you do it right, it ends up giving you an integral that's much easier to deal with than something like this. I would have no clue what to do with this other than to rewrite it using partial fractions decomposition. Now here I want to introduce you to a problem. If any of you are sort of familiar with, especially like old school video games, there's always sort of a final boss you have to defeat at the end. And so we're going to think of this problem as being sort of our final boss that we want to defeat before we finish talking about partial fractions decomposition. I'm going to get you started, and actually you're going to complete this as part of a written assignment to be submitted in the course. So imagine that you were asked to find this antiderivative, right, to compute this integral. So just to see how we would get started, right, anytime we're dealing with this sort of problem, right, our first step is going to be to rewrite using partial fractions decomposition, which I will often abbreviate as Ph.D, not personal flotation device, but partial fractions decomposition. And so in this case, right, if I look at my factors, I've got an x minus 2, single linear factor, and an x squared plus 4, an irreducible quadratic factor. So when I look at this, I'm probably going to want to set this up in the following way. All right. Okay, so I want a1 divided by x minus 2, that single linear factor, and then plus a2x plus b2 divided by that irreducible quadratic factor x squared plus 4. Both of the factors only appear to the first power, so we only need one piece for each of them, but we do need one piece for each of the distinct factors. All right, so what I'm going to ask you to write down and submit is the following. I first want you to find a1, a2, and b2. Okay. Once you have found a1, a2, and b2, you'll have particular values. I'm not going to tell you what they are yet, right? Or you're going to figure that out on your own. But once you have that, you'll then be able to break this integral apart so that it is the integral of some constant over x minus 2 plus the integral of a2x plus b2 divided by x squared plus 4. Now, we're actually going to take this first integral you should be able to compute directly. This second integral, line isn't quite showing up there. This second integral, we're actually going to break apart further. We're going to break it into two pieces. So we're going to first deal with the a2, so that's a constant, over x times x squared plus 4. So that's sort of taking these pieces here, plus taking these pieces. So plus b2 times the integral of 1 over x squared plus 4 dx. Now, this integral, you have a method of integration for solving. Maybe I'll give you a small hint by saying, well, that x squared plus 4, its derivative would be 2x, and that's almost sitting right there. So we have a method of integration to help with that. When I look at this other integral, I don't quite have a function in its derivative, but I do see an x squared plus 4, and I might know some trig identities that could help there. Okay? So your goal in your written assignment will be to fully compute this integral by first rewriting using partial fractions decomposition, and then computing all necessary integrals after you've rewritten it. You're going to have homework problems to help you practice this first if you want to get in some practice where you have some automatic feedback before you do the written assignment. But you now have all the tools necessary to do this and to show off your skills, not only using partial fractions decomposition, but also other methods of integration.